In this video, we will study the performance of short transmission line. That is, we will learn how to calculate voltage regulation, line losses, and transmission efficiency for short transmission line. Now, what are the parameters of short transmission line? As we know, in a transmission line, four parameters can be present. One is series resistance, series inductance, shunt conductance, and shunt capacitance. These four parameters can be present in a transmission line. But in case of short transmission line, shunt conductance is assumed 0. Why? Because in short transmission line, it is considered that there is no leakage current flowing from conductor to earth. Therefore, we assume shunt conductance effect is 0, right? Second, the parameter shunt capacitance, its effect is also assumed 0. Since capacitors are connected in parallel and its value is proportional to the line length. Therefore, when the length of the line is short, there will be less shunt capacitance. Here we can see the total capacitance value. If the length is more, then there will be more capacitor added here and the capacitance value will be more. Let's say this is for first 1 kilometer, this is for second 1 kilometer, this is for third 1 kilometer. If we increase the length, then capacitance value will be added. In case of short transmission line, there is less capacitance, right? It might be up to 4, it might be up to 2. So we will get less amount of capacitance, right? So what we can do, we can ignore the shunt capacitance value and capacitance dependent parameters calculation in the short transmission line, right? For example, one capacitance dependent parameter, which is charging current, its value will be less since the calculation of charging current is dependent on the capacitance and voltage level. And in case of short transmission line, both capacitance and voltage level are less. So ultimately, the charging current, its value will be less. So in case of short transmission line calculation, we can neglect the inclusion of charging current, right? So this is the reason why by neglecting shunt capacitance, it is possible to obtain reasonable accuracy in short transmission line calculation. So we consider only two parameters. One is series resistance, another is series inductance in the short transmission line calculation, right? Now, equivalent circuit of a single phase short transmission line. As we have already discussed, in a short transmission line, two transmission line parameters are considered. One is series resistance and another is series inductance. So there will be two parameters which are resistance and inductance, and these two parameters are connected in series in short transmission line, right? So there will be two parameters. Here is resistance and here is inductive reactance, and both parameters are connected in series. This is the sending end, right? And this is the receiving end. So what is sending end and receiving end? The end where the voltage supply source is connected is known as sending end. So here the voltage supply source Vs is connected. So this end is called sending end, right? And the end of the line where the load is connected is called receiving end. So in this end, one load is connected. So this is the receiving end, right? Now we consider Vs is the sending end voltage, I is the load current, R is the loop resistance, XL is the loop inductive reactance, VR is the receiving end voltage, right? This is VR, receiving end voltage, and this load is inductive load. That means this load is lagging load, right? Now, so as we see in a single phase short transmission line, there are two conductors. One is line conductor and another is neutral conductor. So both are conductors. So each of these conductor has resistance as well as inductive reactance. So it has resistance, right? This conductor also has resistance because this is conductor, and inductive reactance, right? So what we do in short transmission line or transmission line, it is considered that the parameters of both conductors, that means resistance and inductive reactance, are lumped into one conductor. So let's say this is R by 2, this is XL by 2 for line conductor, and for neutral conductor this is R by 2, this is XL by 2, right? So what we do, the resistance and inductive reactance both are lumped into one conductor. So return conductor R by 2 and line conductor R by 2 is added together, so we get R, and return conductor XL by 2 and line conductor XL by 2 are added together, so we get XL. That means we lumped both resistance and reactance in one conductor in line conductor, right? And there will be no resistance and reactance in the return conductor. That's why this R is called loop resistance, because this is the resistance of both conductor, right? The resistance of return conductor or neutral conductor as well as the resistance of line conductor, right? Both line conductor resistance are added together, which is called loop resistance. Similarly, XL is called loop inductive reactance because this inductive reactance is the inductive reactance of both conductors, right? Therefore, this R is called loop resistance and this XL is called loop inductance, right? Now, how to draw a Phasor diagram of a single phase short transmission line. Here is the equivalent circuit of single phase short transmission line. R and XL are connected in series. Load is inductive load and VR is the receiving end voltage. Vs is the sending end voltage, and this is a series circuit, right? So from this equivalent circuit we can write Vs, which is the sending end voltage, is equal to IR plus IXL plus VR, right? Now how to draw Phasor diagram? So in Phasor diagram we have to draw all the voltage phasor and the current phasor I, right? Now for drawing Phasor diagram we consider current I as the reference phasor, so we draw current I, right? Next we start from voltage VR. So VR is across the inductive load, so VR leads current I by phi R. We assume phi R is the angle between VR and I, right? So this VR is represented by OA in this diagram. Next we draw voltage IR. So this voltage is parallel to the current, right? Because this is purely resistive drop. So this is parallel to the current, this is current, and this is the voltage drop, right? Next we will draw IXL. So if I is here, then for drawing IXL, this IXL leads current I by 90 degree, so we can draw like this. And finally we can draw the sum of VR, IR and IXL as Vs like this. And we consider phi s is the angle between sending in voltage and current, right? So this is phi s. By this way, we can represent the voltage and current phasor in the phasor diagram of a short transmission line. So in the previous slide, we have drawn phasor diagram using current as reference. Here the phasor diagrams are drawn for a short transmission line, while VR, which is the receiving end voltage, is taken as reference. So here VR is taken as reference, and this is for inductive load. Load power factor is 70% lagging. Here VR is taken as reference, and this is for resistive load, right? And here also VR is taken as reference, and here load is considered as capacitive load, so power factor is considered as leading power factor, right? So the calculations we are doing in this study for short transmission line, it is for inductive load. You can easily do the short transmission line calculations based on different loading power factor conditions. For example, for leading power factor or capacitive load, you can use this phasor diagram, and for resistive load you can use this phasor diagram, right? Now we will find how to determine voltage regulation, line loss, and transmission efficiency of short transmission line. Here is the single line diagram, and from this single line diagram, according to the Pythagorean theorem, we can write OC square equal to OD square plus DC square, right? So OC is Vs, so Vs square equal to OD is OE plus ED, so OE plus ED whole square, and DC is DB plus BC, so DB plus BC whole square, right? Again, OE can be written as VR cos phi, so VR cos phi, and ED can be written as IR, right? ED and IR are equal, and DV can be written as VR sin phi r, right? And VC, it can be written as IXL, right? So ultimately we get Vs sending in voltage equal to square root of VR cos phi r plus IR whole square plus VR sin phi r plus IXL whole square, right? So we get the sending in voltage, we know the receiving in voltage VR. So what is the equation to determine voltage regulation? Vs minus VR divided by VR multiplied by 100, since percentage of voltage regulation. So this is the value of Vs VR, right? For sending in power factor, what is the sending in power factor? Power factor is equal to cos theta. Here theta is equal to phi s, which is the angle between sending in voltage and current. So we write cos phi s is equal to OD. From this phasor diagram we find cos phi s is equal to OD divided by OC, right? base divided by hypotenuse. Again, OD is equal to OE plus ED. So we can write VR cos phi r plus IR, right? And OC is equal to VS. So we can write VS here. So this is the sending in power factor, which is cos phi s. Now the power delivered, this is the power delivered in the load, VR IR cos phi r, right? And the line losses will be I square r due to this resistance, right? So the total power sent out will be line losses plus power in the load, which is VR IR cos phi r, and line losses is I square r. So total power sent is equal to VR IR cos phi r plus I square r, right? And what will be the transmission efficiency? So we know the equation for transmission efficiency. So what will be the percentage of transmission efficiency? We know the equation for transmission efficiency, which is power delivered divided by power sent out multiplied by 100. So here power delivered is VRIR cos phi r and power sent out is VRIR cos phi r plus I square r multiplied by 100. So by this way we can get all the equation to determine voltage regulation, sending in power factor, power delivered, line losses, power sent out, and transmission efficiency for short transmission line. Now here is a problem on short transmission line. A single phase overhead transmission line delivers 1100 kilowatt at 33 kV at 0.8 power factor lagging. The total resistance and inductive reactance of the line are 10 ohms and 15 ohms respectively. Determined sending in voltage, that means Vs, sending in power factor cos phi s, right? And transmission efficiency. The parameters given are resistance 10 ohms, right? Reactance of the line 15 ohms, power delivered 1100 kilowatt, then receiving end voltage, which is 33 kV, right? And receiving in power factor cos phi r, which is given as 0.8 power factor lagging. So we know the formula to determine sending in voltage, sending in power factor, and transmission efficiency, right? So this is the equation to determine sending in voltage. Vs equal to square root of Vr cos phi r plus Ir whole square plus Vr sin phi r plus Ixl whole square, right? So here Vr is given, cos phi r it is given, IR, here I is not given, right? But R is also given. So we have to determine I, which is not given, right? Similarly, here VR is given. So cos phi r is given, so we can easily determine sin phi r from cos phi r, right? I is not given, we have to determine, right? XL is also given. So only parameters we have to calculate here is I, right? And rest of the values are given. Similarly, for determining sending in power factor cos phi s, only we have to calculate I value, right? Similarly, for transmission efficiency, we have to find out I value. That means if we find out I value, then we can easily determine all the three parameters which we have to determine, right? Now we can easily determine the value of current by using this formula, power delivered equal to VR IR cos phi r. Here power delivered value is given, VR is given, cos phi r is given, so we can easily determine IR, which is I, right? And also we can determine the value of sin phi r from this cos phi r, right? So we can easily determine phi r from here and then sin phi r, right? So after putting all the values, we get the sending end voltage as 33709 volt. Similarly, after putting all the values, we get the sending in power factor 0.9955, which is lagging power factor, right? Similarly, after putting all the values, we get the transmission efficiency as 98.44%.